The first thing that shows up in section 4.3 actually comes in handy quite a bit. This thing called the conjugate zeros theorem, where if you know that a plus bi is a zero of the polynomial function, then so is a minus bi. And this first example is to show how this works, but this really does show up pretty often. If you have any sort of complex roots, this thing comes in handy a lot. So for this first example, we want to find a cubic polynomial, so I want a degree 3, real coefficients, and where 1 and 3 plus 2i are both going to be zeros of that polynomial function. Okay, well, right off the bat, it's the thing that's in red right here. If 3 plus 2i is a 0, so is 3 minus 2i. So that would mean that x minus 1, x minus the quantity 3 plus 2i, and x minus the quantity 3 minus 2i would all have to be factors of that polynomial. So that's why I have it set up this way, where those factors are all right there. Right? That's what would have to happen for those three numbers to all be zeros. And then from there, you just have to multiply it out. The strategy for multiplying it out is take care of the complex conjugates first. This will get a lot uglier if you don't. So that's why I leave the x minus 1 alone, like how this just keeps getting copied down. And right away, I just dealt with this, where you multiply these two factors that have the complex conjugates in them. So what I ended up doing was, if you kind of follow along with what I've got here, I foiled it, although foiling it ends up being sort of complex when you have complex numbers. So x times x would give you the x squared. Then this term and this term are the outer. So if you multiplied x by minus 3 plus 2i, you'd get minus 3x plus 2ix. And then the inner would be minus 3 minus 2i times x. So minus 3 times x minus 2i times x. And then these last four terms are the last part of the FOIL. So it's the minus the quantity 3 plus 2i times minus the quantity 3 minus 2i, which would be the same thing as 3 plus 2i times 3 minus 2i, and you have to FOIL that. So 3 times 3 will give you the 9. The outer, which would be 3 times negative 2i, is minus 6i. The inner, which is 2i times 3, is 6i. And the last, the 2i times negative 2i, is negative 4i squared. We can simplify some stuff, right? We've got some terms that are going to add out. And then down here, I have a 4 at the very end, and that's because I squared is equal to negative 1. So the negative 4 times negative 1 gives you that 4. So I tried to keep the number of simplification steps under control, but that does also mean that a few things happen in every individual step. So that's what's going on there. I mean, this thing's really long, but it's just sort of the nature of the beast when you've got complex conjugate roots. There's no way to shorten that up. At least there are some terms where you get the additive inverses, so you can cancel them out right there, and then down here, the 6i and the negative 6i. And then having to rewrite I squared as negative 1, that's also a common thing when you have the complex conjugate roots. So to get from that negative 4i squared to just 4. But then this, you could rewrite as x squared minus 6x plus 13. And then from there, I just distributed x squared minus 6x plus 13 through the x minus 1. So this first part is multiplying the trinomial by x, and then down here is multiplying it by minus 1, and then combining like terms together, you end up with this as the final answer, x cubed minus 7x squared plus 19x minus 13. This stuff that's in the middle of this page about the fundamental theorem of algebra and then the number of zeros theorem, there always has to be at least one complex zero, and at most the number of complex zeros can match up with the degree of the polynomial, but you can have less than that. So you can have less than n. I guess the easy example would be like, what if your polynomial function was x squared minus 2x plus 1? Then it's really just x minus 1 quantity squared. So it's a degree 2 polynomial that just has one root that's repeated twice. But that sort of thing can happen where you can have repeated roots. And that's where you end up with less than n distinct roots, as if you have repeated roots somewhere. But with this example down here, we've got 3 distinct roots. So we're thinking, well, then the degree must be at least 3, and it'll be exactly 3 because none of those roots are going to be repeated Although I guess you could make a more complex function if you really wanted to and have that sort of thing going on. But if 1 is going to be a root, then x minus 1 needs to be a factor of the polynomial. Then if negative 1 is a root, x plus 1's got to be a factor of the polynomial. And then if 0 is a root, then x has got to be a factor of the polynomial. So then what's the c for up in the beginning, up in the front? That's to take care of this, the idea that f of 2 has to work out to be negative 3. So this c up front, it's just some constant, it's just some number, so it's not going to have any effect on what the roots are. But that's how we can make the right adjustment to make sure that f of 2 is equal to negative 3. That's what that's for. Because then if we substitute in a 2, so I just subbed in, like here you'd get 2 minus 1, which is 1, and then here you'd get 3, and then here you get 2. So then 6c would have to be equal to negative 3. So for this to work out right, we're going to need c to be negative 1/2. And so then I just rewrote f with negative 1/2 instead of c. Multiply x minus 1 and x plus 1, that's x squared minus 1. And then you just have to distribute the negative 1/2 x through that, and you get what's down here, the negative 1/2 x cubed plus 1/2 x. So the thing with this one that's a little bit different is that you need that c in order to get this condition down here to work out right. You've got to solve for that. Number 3 is basically the same idea as number 2, just a little bit longer, I think, because the zeros don't work out quite as nicely, right? This is easier when they're 1, 0, negative 1 than when they're 2, 5, and negative 3. But it's the same concept. If 2 is going to be a 0, we need x minus 2 as a factor. 5 is going to be a 0, we need x minus 5 as a factor. Negative 3 is going to be a 0, we need x plus 3. Then you got to have that c out front to take care of this condition at the end, that f of 1's got to be negative 4. Okay, well then we'll figure out what f of 1 is, and if we sub in, eventually what you end up with is that 16c is negative 4. So then c would have to be negative 1/4 to get that condition to work out right. Okay, well then we've got this, which we now have to multiply out. So I just multiplied x minus 2 and x minus 5 first to get this trinomial. Then I distributed the x plus 3 through this trinomial, right? Because there's the distributing x, and then here, down here is the distributing the 3. Combine like terms, and then distribute the negative 1/4, and you end up with that as a final answer, that f of x is negative 1/4 x cubed plus x squared plus 11/4 x minus 15/2. Number 4 is a slightly different kind of problem, although certainly thematically related, where we know what one of the zeros is. So we know that 1 is a 0 of this function, and we have to find the remaining zeros. Maybe there's just one other remaining 0 that's repeated twice, or maybe there are 2 distinct other zeros. Couldn't be more than that, right? Since the degree of the polynomial is 3. But if 1 is a 0, x minus 1's got to be a factor of this thing. So what I did to save space is I did it with synthetic division. So that's why I've got the 1 over here, right? That's how you would divide by x minus 1, the short way, right? To use synthetic division. And then here are the coefficients of the polynomial. So you bring the 1 down, you do synthetic division, and then you can rewrite f of x. You can say, well then, 1, negative 4, 13, there's where that's going to show up. That's going to be a factor of that polynomial. So that's what you get when you multiply x minus 1 by this. You should get the original polynomial back out. So you've got x minus 1 times x squared minus 4x plus 13. We know what the root of that is, the x minus 1. So then we just got to get the roots of this. That doesn't factor, so you're going to want the quadratic formula here. So factoring that would be ideal, but we can't do it the usual nice way. So I use the quadratic formula. I guess you could do it by completing the square if you wanted to. There's nothing wrong with that. But I think most people go for the quadratic formula here, so that was the reason I picked it. But then you substitute in, simplify it down a little bit. You get a negative underneath the radical, but 36 is a perfect square. So the square root of negative 36 is 6i. So you end up over here, where you have 4 plus or minus 6i over 2. So really that ends up being 2 plus or minus 3i. So those are the other 2 remaining zeros, 2 plus 3i and 2 minus 3i, because those are the zeros or the roots of this piece up here, the x squared minus 4x plus 13. So then that's all of the zeros, right? We have 3 distinct zeros, the polynomial's degree 3, so there couldn't possibly be more than that. Number 5 is like number 4, except the polynomial's of higher degree. So it seems like that's going to make this longer, right? This polynomial's degree 4. But our one known 0 is complex, so you can use the conjugate zeros theorem to get a second one right away. So we know that negative 5i is a 0, but its complex conjugate is positive 5i. That's also got to be a 0. So there are two zeros right away, and we should be thinking, like, we should be expecting 4, just because the degree of the polynomial is 4. You think, okay, that's probably going to match up. Unless we get a repeated root, we're going to get 4. So, okay, fine. Then if we multiply x plus 5i and x minus 5i, because both of these individually would have to be factors of f of x up toward the top. But if we multiply this out, this will give us something to divide by, and then we can factor whatever's left, whatever quotient we get. So if we FOIL this out, you get x squared minus 25i squared, but I squared is negative 1, so that's x squared plus 25. You can't use synthetic division here because the thing that you're dividing by is going to have degree 2. It's got an x squared in it. So you got to do it with long division, and I guess the other thing to be careful with is there's no x term, so you want to put a 0x in there, so that way you don't get things all misaligned in the division. But then if you go through and do the long division, it works out to be 2x squared minus 2x plus 5, and then we just have to factor that. So this is what we're left with now. We know that f of x is equal to x squared plus 25 times 2x squared minus 2x plus 5. So now we just have to factor this piece right here, the 2x squared minus 2x plus 5. This is another one that's not going to factor nicely. So quadratic formula again, substitute in, you get the same thing underneath the radical that we had in the last example. I guess that's sort of nice. So we already know what that is. That's 6i. So you have 2 plus or minus 6i over 4. So that's 1 plus or minus 3i over 2. And if you want to write it with distinct real and imaginary parts, I rewrote the two numbers that way here, where it's 1/2 plus 3/2 i, 1/2 minus 3/2 i. And those are the other two zeros. So I circled them all in red, and that's why there's the 3 and the 4, because we already had the first and second ones up top. So there's the third, there's the fourth. We can't have any more than that because the polynomial is degree 4, so we're done. On page 4 with examples 6, 7, and 8, these extra constraints up here actually help. Leading coefficient of 1, that's the simplest thing that could possibly happen. Least possible degree, also keeping it as simple as we can. And then basically we're just given a couple of zeros and we've got to get a polynomial that has those zeros. And basically the simplest one that we can. So if x is a 0, x minus 6 must be a factor of the polynomial. And if negative 2 is a 0, x plus 2 must be a factor. That's really about all you need here. If you multiply this out, so if you just FOIL it, you get x squared minus 4x minus 12. And that's pretty much it, right? We've got the right leading coefficient. We've got a 1x squared. We have the least possible degree because we have two distinct roots, and then we have degree 2. So, oh, and I guess we have real coefficients, right? We don't have imaginary coefficients there. So we're good to go. So number 6 is nice and short. Number 7's a little bit longer than that, but it's not too bad. The thing to keep in mind is that complex conjugates theorem again, where you go, 3i. If that's a 0, so it's negative 3i. That means we got 3 of them. We've got 2, 3i, negative 3i. So that's why I've got this, right? If 2 is a root, x minus 2 must be a factor. 3i is a root, x minus 3i must be a factor. And if negative 3i is a root, x plus 3i. And again with the multiplication, take care of the ones with the complex conjugates first. It's much easier. So notice I left the x minus 2 alone at first. I multiplied out the other two, which would give you x squared minus 9i squared, but I squared is negative 1. So you could rewrite that as x squared plus 9. And then from here, you could FOIL these. You'll end up here with x cubed plus 9x minus 2x squared minus 18. And then I just rearrange it to make it look nice where the exponents are in decreasing order. But that's pretty much it. Then example 8 has something interesting where we have multiplicity 2. Okay, well, I guess first of all, the other root is complex, right? It's 1 plus 2i. So here it is again. We got that complex conjugate theorem. If 1 plus 2i is a 0, so it's 1 minus 2i. So we're going to have x minus the quantity 1 plus 2i as a factor of the polynomial. Also, we're going to have x minus the quantity 1 minus 2i, and then 2 is a 0 with multiplicity 2. So I need an x minus 2, but because it's multiplicity 2, I guess you could view it as either I need a couple of x minus 2's or I need an x minus 2 quantity squared, which is how most people would write that. So then it's this, we just have to multiply it all the way out. Okay. Again, probably want to aim for the complex conjugates first. If you multiply these two together, you end up here, the x squared minus 2x plus 5. And then the x squared minus 4x plus 4 is coming from x minus 2 quantity squared. So if you multiply x minus 2 and x minus 2, you FOIL that out, you'll end up here. And then you've got to multiply these. So I distributed the first trinomial through the second one. So I've got x squared times second trinomial minus 2x times second trinomial plus 5 times second trinomial. And then distributing x squared, negative 2x, and 5 is what's in this line. And then from there, you can combine like terms in a few different spots, and eventually you get x to the fourth minus 6x cubed plus 17x squared minus 28x plus 20. Sketching graphs by hand. These are fun, and they come up in handy later because then you can anticipate a lot of other stuff that happens later in this section. So if you have a 0 of multiplicity 1, the graph's going to cross the axis there. But if you have a 0 of even multiplicity, the graph is tangent to the axis. So what does that mean? It means it touches it, but then it stays on the same side. It doesn't cross it at all. So if it's underneath, I guess to the left of where the 0 is, it'll be underneath on the right side as well. And then what's this about? You have a 0 of odd multiplicity but greater than 1, so like multiplicity 3, 5, 7, that kind of thing. Then the graph crosses the x-axis and is tangent to the x-axis. So what happens there, and this is a hard one to draw and we're not really going to deal with it, but what happens is that the graph will cross, but right where it's crossing, it kind of flattens out, so that way you get that tangent effect too. But for what we're going to do, just worry about the first two. So the way that I would think about it is crosses with multiplicity 1, touches with multiplicity 2, really with even multiplicity. But that's kind of the way that I think about it. And you can see how I have it written with crosses and touches. So yeah, that's the way that I think. So with this here, we've got p of x is 2x minus 5 times x plus 4 quantity squared. All right, so what are our zeros? Well, from the 2x minus 5, you get 5 halves. That's a 0. From the x minus 4, you get x equals negative 4. So, well, the first thing that I would have done with this graph is I would have just put in these dots, like one right there for the 5 halves, since that's 2.5, right, if you rewrite it as a mixed number. And then the one right there is for the negative 4. And then I said, all right, well, the 5 halves, it's multiplicity 1, so the graph should cross the axis, so that's what's going on there. And then multiplicity 2 at negative 4, so it touches but doesn't cross, right? So the other thing is, well, how do you know what side you're supposed to be on, right? How do you know that it's not above in the middle, below over here, and then I guess also above over here, right? How do I know that I have this right? Because I got the y-intercept. The y-intercept is actually really helpful here because that gives you sort of a point to start with. So I said, all right, the y-intercept, if you just sub in 0, you're going to get negative 5 times 4 squared, so it's negative 5 times 16, that's negative 80. So I just had to kind of pretend that that's negative 80, even though it looks more like it's about negative 6. But the graph's just not big enough to do it to scale. So I don't think I would worry about it too much. And the ones in the homework kind of look like this too. But then if you say, okay, well, we know this point's down here. So then if it's going to cross there, then it's just got to come up and cross like that. But then we know at negative 4, it's just going to touch. So it's got to go up to negative 4, touch, and then stay below the axis over there. And that'll give you a sketch of what that graph would look like. It probably isn't going to be perfect, but it's going to be pretty close. Then number 10, similar sort of idea, except with number 10, they both have even multiplicity, both roots. So that means that we're staying on one side the whole time. So our zeros, 3 for the x minus 3 quantity squared, 1 for the x minus 1 quantity squared. Both of them have multiplicity too. So in both cases, the graph's going to touch the axis but not cross it. And then we just have to figure, well, are we above or are we below? Well, what's the y-intercept? P of 0 You get negative 3 quantity squared times negative 1 quantity squared. So it's going to be 9 times 1, which is 9. That's positive. So we go, all right, we know we're up here. And again, I know this isn't really 9. You have to kind of use your imagination a little bit. The graph isn't big enough. But from there, you say, okay, well, it's got a touch at 1. So we come down here, touch at 1, but doesn't cross. So it'll stay on this side, but then it has to come back down again and touch at 3. And then it's going to stay on this side, so it's just going to keep going up after that. So you get sort of a W shape out of this graph. On this page, I guess the first half of the page or so, it just has these pre-made graphs in here. I just wanted to point out what these graphs actually look like that you make on the last page. So this version, this one here in the upper left, that's a zoomed in version of this. So this is one where you can kind of see, I mean, it's a little grainy, but where that's an 80 right there that my cursor is pointing at. So that's supposed to be where the y-intercept is negative 80. So this thing is much thinner than what we had when we sketched it, but it's the same sort of shape, right? And that's why I zoomed it in to make it a little more obvious that that's what that shape looks like. But then the one for example 10, yeah, that's what ours look like, right? There's the W. So looks like we pretty much got that one. All right, so that's really just all that's about, just to say, look, what we used, which didn't feel like it was a whole lot of information, is actually enough to get a pretty good looking graph. And then number 11 at the bottom of the page here, this is one where it's like what's on the last page, but backwards. So instead of here's the function, sketch its graph, it's here's the graph, figure out what the function must be. So if that's our graph, if you look at that, you go, well, it looks like there are 3 zeros. There are 3 points where that's crossing the x-axis. So 1, 2, and then negative 2. All right, so up here we've got our 3 zeros, and it's crossing every time, right? There's never a case where it touches and then stays on the same side, right? Below to above, above to below, below to above. So crosses, crosses, crosses. So multiplicity 1 in all 3 cases because it's crossing every single time. And then the other thing that we're going to need is the y-intercept in order to get, basically in order to get the numbers to work out the way that we need them to in the function. So this is kind of going back toward the beginning of this section where we had the c, and then we had that initial condition where you could solve for c by using that. That's kind of what we're doing here. So the y-intercept, if you look at it, it's right there. So it's 2. So f of 0 is 2. And then here's that thing with the c, right? So if x minus 2 is a 0, you got to have x plus 2 as a factor, and then the x minus 1 and x minus 2, similarly for the other zeros. And then you need that c out front just to make sure we can get f of 0 equal to 2. So then if we solve for c, so subbing in 0 for x in all 3 spots there, you end up with 4c is equal to 2, so c is 1/2. All right, well then f of x would be 1/2 times x plus 2 times x minus 1 times x minus 2. You can multiply that part out if you want to, but the concept part we've got, and I don't really have the room underneath that to multiply it out. So for that reason, I kind of just left this one factored.